was told to have 6 slides, so I stuck to the schedule. So I will talk to the issues more than. So the presentation is on development of high performance graphene mercury cadmium telluride detector technology for midwave inverter applications. It's a NASA program, and my colleagues are John Zeller from Magnolia, and we are collaborating with 2 gentlemen from the University of Virginia. It's Samiran Ganguly, who's a postdoc, and the professor is Abhi Ghosh. And we're also working very closely with Harminder Woman and Sachi Babu, both of them at NASA Ashok, and they are the reason we are working in this particular area. And we're also collaborating with another gentleman, Dr. Naveen Bhar. He is with the Army Night Vision Electro-Optical Sensor Directorate, and he's been in this area for many, many years. So the idea really is that people know about graphene. That's a new material that is being looked upon for various applications. And mercury cadmium telluride detector technology is known for a lot of applications. So I only have 6 charts, so I won't take too much time. The idea really is that we're trying to demonstrate high performance detector technology which we're trying to develop for midwave IR for the NASA ESTO health science application. Now, the graphene is a material that we have studied for quite a bit, and we have quite a bit of the published data and a chapter in the book on the application of graphene. And we are also working collaborating in the thyroid area technology with the Night Vision Lab for the detector technology, and thyroid is a well-known material for shortwave, midwave, and longwave. It covers all sort of spectrums, depending on the combination of mercury versus cadmium. Most people know all that. For the midwave, the ratio of mercury and cadmium is about 1/3, and if you go to longer wavelength application, potentially, when you get down to a different composition. And the idea behind this program is we're looking to develop a technology that will operate at room temperature rather than cooling the detectors to get the high performance. And the idea is that we can develop a detector array with a reduced size, weight, and power for MWIR applications, that is a 2 to 5 micron band, and so forth, for remote sensing and for small satellite applications. Next chart. So here is the concept. As I mentioned earlier, mercury cadmium telluride is a well-known material, and the approach that has been developed, which has been studied quite a bit. Many years ago, I worked on it myself, but the Army has been working on developing this technology on a silicon substrate. Rather than using a small substrate and silicon substrate, and then you can put a very thin buffer layer of cadmium telluride for lattice matching, and then you can grow the mercury cadmium telluride material on top of it as an infrared detector material. And then obviously the idea really here is that as the photons come in, the whole electron pairs will be separated, and the graphene is being used to transfer the electrons quickly and be done at a higher temperature. And then the signal can be, if it was a 2-dimensional array down the road, once the device is demonstrated, one can go to put into the relapse circuit, and there are a lot of knowledge about relapse circuit. So the technique that we are using, what we use in this area is to grow mercury telluride using NDE, molecular method, and to demonstrate this performance. Can I go next slide, please? So the device structure that I mentioned, I showed earlier, it's a graphene mercury telluride, and so the gauge is basically silicon telluride, and the absorbing material, as I indicated, is mercury telluride, and the channel that we are using here is graphene, which allows for very high mobility, very low noise, transfer the coordinate carries onto the electrical signal onto the VDOT circuit. So that's the general idea we're trying to work on. We have done a lot of design and modeling work in this area, but because of time, I didn't want to put too many charts in there. But if anybody's interested, I'm happy to provide them a lot more information. We've been working with the design work, and we have done a lot of modeling to show that this kind of device structure is feasible for this performance. Can I go to the next slide, please? So this talks about the effective activity in this presentation. I talked about the operating principles and so forth. And the idea really is, as I indicated, when the photons come in, you generate the carriers. And the idea is to separate the whole electron pairs. And the carriers are transported, inductive carriers are transported to the graphene. And then that signal can be, if it's a two-dimensional, it can be sent out to VDOT circuit, ROIC. So the knowledge base basically here is mercury carrier on silicon, and the VDOT circuit backup is quite well known. However, the idea of using graphene with mercury telluride to minimize the loss of signal and also doing it at room temperature. That's the exciting part, so one does not have to hold these devices. Next slide, please. So, in summary, I try to be on schedule there. So, the idea really here is we are working on, and as I indicated, we have a lot of data modeling-wise, and we are just trying to make these graphene things, and we are using a very high doping graphene bilayers, and we have done the doping work. One thing I wanted to mention is Magnolia, we are located in Google, Massachusetts, but we also are co-located in Albany at the Albany Nanotech Center, which is a $20 billion investment in the microelectronics area. We are co-located there, and they do a lot of work in graphene for integrated circuits. So we are doing the design work for the graphene, bilayer graphene, to dope it to very high doping, and then to integrate that eventually to multi-thyroid detector arrays and so forth. So there's quite a bit of measurements done as data, and we'll be publishing that work. And if anybody's interested, we are happy to provide more information on that. This is my first time to give a talk in this style, so I wanted to be careful. I didn't assume there. Again, the idea here is for the earth science application, combine the best of both materials, and the improvement in carrier mobility and lifetime of our gas will enable the enhanced IR signal performance. And our goal really in this program is to demonstrate high performance mercury telluride graphene based detectors at room temperature covering the 2 to 5 microns, and then eventually the focal point arrays with weight and power to benefit the I think that's my last chart. Thank you very much.